Hello. Today we're going to talk about discrete dynamical systems. In particular, we'll focus in this lecture on the linear case. Dynamical systems that are discrete are interesting in their own right, but also give a great gateway into thinking about ideas like chaos. Um, so let's explore these dynamical systems, and we'll start pretty simply, and then we'll get to some slightly more advanced topics. The linear case is fairly well behaved. In next lecture, we'll talk about the nonlinear case, which is arguably quite a bit more interesting. But this one is still pretty interesting as well. So let's start off with maybe a very simple dynamical system, which is in the form of what's called a recurrence relation. So this idea is that if I take some previous, if I know some previous number, I can get a new number. And in this case, it's just I'm multiplying by 5. Of course, I have to start somewhere. So let's start with x0 is equal to 1 as our initial condition. So this is our initial condition, and this is our dynamical system. All right. So, of course, getting the first few values of these is pretty straightforward. For instance, if we want x1, then by our dynamical system, maybe this is, we'll call it a recurrence relation. All right. So x1 is just, of course, we can write this as x0 plus 1. That's just being an index. And then by our recurrence relation, this is 5 times x0, and x0 is 1, so we have something like that. If we had a different initial condition, such as 3, then we would just get something like this, 15, a little more interesting. x2 then, so maybe we'll just keep this in the form 5 times 3, instead of thinking about it as 15. This is just, right, this is 5 times x1. And we can use the same trick we had before. We say that this is just 5 times 5 times 3, because that's x1 is 5 times 3. And then this will be 5 squared times 3. And I think you can pretty quickly see the general case will be 5 to the n times 3. All right, but this pretty simple example gives us kind of a picture about how to do more complicated things. So first of all, this is what we call a closed form. That is, if I wanted to find, say, the 1 millionth entry, well, I could keep multiplying by 5 and do many, many steps. Or I could just raise 5 to the 1 millionth power, be something very large, but whatever, then multiply by 3. So that's what we mean by a closed form, that we can just, we don't have to build all the way up to some arbitrary value. We can just plug in this case, n, and get the solution. Okay, so hopefully that one was pretty straightforward. Let's take a look at, excuse me, at something a little more interesting. So maybe the most famous one in this case is the Fibonacci sequence, introduced by Leonardo of Pisa, who was sometimes called Filius Bonacci, which was shortened to Fibonacci. He was the guy who introduced Arabic numerals. Those are the 0 through 9 numbers that we use every day. He introduced those to the Western world, which got us over using things like Roman numerals, which are much harder to, for instance, to multiply things with. So anyway, he did many things, but in particular, he introduced the sequence. Notice if we want to do it, so for instance, if I want to get started, I need to know, say, a starting value. Let's say f0 is 0. But even then, if I want to get, say, say 1 or f2 or something, I need to know the 2 previous values. So that is, I need a second starting value, second initial condition. Let's say, sorry, f1 is 1. These are some of the normal ones. Sometimes you might see it start with 1, 1, but as you'll see, that generates the same sequence, just labeled differently. So this is the Fibonacci sequence, or Fibonacci recurrence relationship. We have our initial conditions here, ICs for initial conditions. And let's just generate the first few. You have probably done this somewhere else, but let's just get a feel for it. So we already have F0 and F1. F2 is then going to be F1 plus F0. F1 is 1, F0 is 0, so we get 1 there. F3 will be F2 plus F1, just using again and again this recurrence relation. But now F2, I need to use the value we just computed, so that was 1. F1, we use the initial condition, that's 1, and so we get 2. And then after that, we won't need the initial conditions anymore. F4, for instance, is F3 plus F2. Well, F3 we computed before, that was 2. F2 we computed before, that was 1, so now we get 3. F5 turns out to be 5, then after that we get 8, 13, and so on. So this sequence has kind of an unusual pattern behind it. Let's see if we can understand a little bit more about that pattern. And the idea is that we can borrow some ideas from differential equations and some ideas from our previous result here. So notice what we had last time was an exponential 5 to the n times some number. In this case, the number just matches the initial condition. But this exponential popped out because we're sort of repeating the same thing over and over. And this might remind you of the idea of, so think of ordinary differential equations, where we have something like y prime is equal to maybe 5 times y, and y at 0 is equal to, say, some initial condition. We know by all kinds of different arguments that the general solution looks like this. This is e to the 5t times the initial data. And notice that in this case, I think sometimes people kind of overlook this. This is just a number to the power t times the initial data, of course. E to the 5 just being some number, right? So that's pretty strongly analogous to this. It's just 5 to the variable we're interested in times the initial data. So, okay, that's how we start with first order ordinary differential equations. For second order ordinary differential equations, for instance, think about something like y double prime plus 5y prime plus 6y is equal to 0. Excuse me. If you recall, the idea is, or ansatz, if you like, is to guess. Is basically to try the same idea again. So here, if we hadn't known in advance, maybe we knew it was something like e to some number times t, then, or maybe say e to the rt is a common guess, we could plug in e to the rt into this thing, and after solving, we would find that r needed to be 5 in order to be a solution. So here, we do the same thing. We guess the solution is something like e to the rt, and after a while, we get, plugging this in, we get 2 derivatives will give us an r squared times e to the rt. One derivative will be r times e to the rt, and the last will be just e to the rt. After dividing by e to the rt, we get r squared plus 5r plus 6 is equal to 0, noting that e to the rt is never 0. And from this, we can extract that we can factor this thing r plus 2, r plus 3, and get that this guy, the solutions here are -2 and -3. So our general solution is then of the form, maybe some number times e to the -2t plus some other number times e to the -3t, like that. So that is the idea, is we have an initial condition, and we, after solving for the possibilities for these roots, we get, we form a linear combination to solve. And then these a's and b's are arbitrary. We can use the initial conditions. If any initial conditions were given for our ordinary differential equation, we can use those to isolate, that is to solve for a and b. Okay, so how does that help us here? Well, this Fibonacci sequence is what's sometimes called a second order recurrence. So this is second order recurrence relationship. relation sometimes. And this previous one is called the first order because you need the previous two pieces of information to figure out what the next one is. If I only know one of the Fibonacci numbers, I can't get the other one. That is, suppose somebody didn't tell me these initial data and just said, okay, well, Fn is 17 or something. What's the next? I need more information than that, right? I need to know the previous two pieces of information. So this second order recurrence relationship might remind us of a second order ODE in some way. A derivative, after all, is just some way of talking about a difference, in that case, sort of an infinitesimal scale difference, but difference nonetheless. And so by analogy, we might guess, so Fn, what we would like is a formula for the nth Fibonacci number that we can just plug in. That is, we want some type of a closed form. So let's try to make a guess. And here our guess will be, Fn will be, it's normally written lambda to some power. Notice that that's just another exponential. It should remind you very strongly of this, just some number to a power, where lambda is to be determined. All right. And if we just plug this guess in, well, let's see, let's write it again, Fn plus 1, Fn plus 2 is equal to Fn plus 1 plus Fn. So if we plug in our guess, this is lambda to the power now, n plus 2 is equal to lambda to the power n plus 1 plus, plus lambda to the n, just plugging that in directly. Okay, let's divide by, notice that there's a common factor of lambda to n, and this is assuming lambda is not 0. If lambda is equal to 0, well, maybe this gives us some type of solution to the recurrence relation. For instance, if lambda was always 0, we could have 0 is equal to 0 plus 0, but that's not very interesting, and also would not match at least one of our initial conditions. So for now, we're just trying to find a solution, so let's assume lambda is not equal to 0. And what do we get? We get lambda squared is equal to lambda plus 1. But this is a quadratic equation, and we can solve it. So maybe writing it in the standard quadratic form, we have something like this. And already some of you might recall this very famous relationship, this polynomial. A number squared is the same as just adding 1 to that number. So let's see what numbers satisfy that. So just using a quadratic formula, here we have negative 1, so positive 1, plus or minus the square root of b squared, that's 1, minus, and then it's 4 times 1 times negative 1, all divided by 2. But if we work that out, that's 1 plus or minus the square root of 5 divided by 2. Right? These two numbers are very famous, especially the one with the plus sign. This is the so-called golden ratio. It's often denoted with the symbol phi. Its brother or sister or cousin or whatever is the one with the minus, and it's often denoted by phi bar. This means the conjugate, the bar here denotes a conjugate, but normally when we think about a conjugate, we think about a conjugate with maybe a complex conjugate. Here, this is a conjugate with respect to square root of 5. Complex conjugate being conjugate with respect to square root of minus 1. But here we think about it as conjugate with respect to minus 5. If you don't like thinking about it that way, that's okay. Just phi bar is a notation for this other root. And then we would guess that, notice that since maybe I should say this, since relation, the recurrence relation, Fn plus 1, plus 2 is equal to Fn plus 1 plus Fn, this thing is linear. That is, the unknowns are just added together. We could consider more general case where maybe they have some scalar multiples, something like this. Would also be considered linear, or it could have some other coefficient here. We just have a nice linear relationship between these coefficients. That means adding two solutions will give let me say more generally, a linear combination of solutions is also a solution. So notice we're not saying at this point that we've satisfied the initial data. We're only trying to satisfy these two things. So let's take a look at that. That is, excuse me, at this stage, we're only trying to satisfy the recurrence relation. So our general guess for Fn, well, lambda to the n was our guess, but we found out that lambda could be phi. So phi to the n will, if you plug it in here, will work. You can double check that. But so will phi bar to the n. And any linear combination of these will also work, where a and b are to be determined. Excuse me, I have a little cough. All right, so, and let's say by the initial conditions, by the initial data, by the ICs. So let's try it. So we have F0. We know F0 was 1. That's from the, I'll just write IC here to remind us that comes from the initial condition. But at the same time, that's A times phi to the 0 plus B times phi bar to the 0 using this relation. So anything to the 0 power other than 0 is just 1. So we get A plus B here. And this tells us automatically that A is equal to minus B. Okay, but we need our other initial condition. So F1 here is equal to 1. If we plug in that to the right-hand side, we get A phi to the 1 plus B phi bar to the 1. And that's just A times phi plus B times phi bar. But we know that A is equal to minus B. So this is A phi minus, excuse me, A phi bar. So this tells us that we get 1 is equal to A. Maybe we can just, I think it's pretty clear, we can just solve from here. This is 1 divided by phi minus phi bar for A. Okay. Phi minus phi bar, though, this is 1 divided by, well, phi bar is 1/2 plus square root of 5 divided by 2. And, excuse me, that's phi. Phi bar is 1/2 minus square root of 5 divided by 2. Notice that we get that the 1/2 halves cancel. We get the minus, and a minus gives us a plus. So we get square root of 5 plus square root of 5 divided by 2. That's just square root of 5. So this is 1 divided by square root of 5. And that means that B is negative 1 divided by square root of 5 because B was just negative A. And so we get a closed form for our Fibonacci sequence. The form, so it's just A, just going up here, excuse me, and filling in the A and B for our formula. So maybe combining these a little bit, we get a square root of 5 on the bottom, excuse me, square root of 5 on the bottom, and then phi to the n minus phi bar to the n. Let's zoom in there a little bit, phi bar to the n, like this. So this is a nice closed formula for the solution. In fact, this has a name. This is Binet's formula. That's by, I think, Jacques Binet, who lived 1786 through 1856. This Binet's formula. It was actually known before Binet. It had been discovered earlier, but he sort of rediscovered it and popularized it. So this is a closed form. Now, if you want to plug in, if you want the millionth Fibonacci number, before our only choice was really just to keep computing out 1,000,000 times and doing this sum of the previous two terms. But here, with this closed form, we can just plug in 1,000,000. We get phi to the 1,000,000, phi into the phi bar to the 1,000,000 divided by square root of 5. That's it. We see a little bit more out of this too. We see kind of a nice structure. So phi bar, if you compute it, it's between 0 and 1. So that means as n goes to infinity, this number gets very small. And so the whole thing is behaving more or less like phi to the n times some constant with a small, minus a small error. So that is the Fibonacci numbers, in a sense, grow exponentially, which is maybe not so obvious when you first look at them. We get this fairly nice relation. There's some other things, like you might have heard that the ratio of successive Fibonacci numbers, so if you look at fn plus 1 divided by fn, this ratio goes to phi as a famous relation, and that comes straight from this Binet formula. So this is not only that, this is a fairly general way to solve these second order and higher order recurrence relations. So again, just to reiterate the sort of important parts here, because we looked at a lot of different steps. Given some recurrence relationship, we can just, the general approach is just to guess that we have some type of exponential function with an unknown base, which is exactly the same idea as in the differential equations case. That gives us some type of polynomial equation to solve. If we can solve that equation, in this case, it came out kind of nice that it was a golden ratio, but just whatever the roots of those happen to be, we now assemble in this way with some unknown coefficients and use the initial conditions to solve, and that gives us a closed formula. This is a fairly general method. We can do a bit more with this method and with this analogy to ordinary differential equations. So I'd like to kind of sketch how that works, maybe not giving completely exhaustive treatment, but just kind of giving you some of the flavor for how to extend these ideas, extend the ideas of differential equations to slightly more maybe interesting settings. So let's see an example here. Xn plus 2, and this is, I guess, an example of a non-homogeneous recurrence relationship. So we have something like 5x to the n plus 1 plus 6x to the n. I mentioned something about that earlier, but before we set it equal to 0 here, this is 24n plus 2. So let's consider this recurrence relation. And I won't give initial conditions right now because it's already this one's already a little bit involved, but if you had two initial conditions, you could use those to get a completely finalized version of this solution. But now we'll just get a sort of a general solution to the equation. And the idea we borrow directly from ordinary differential equations. So first, consider homogeneous equation. And that is xn plus 2 plus 5xn plus 1 plus 6xn. But to make it homogeneous, we'll put the right-hand side equal to 0. So notice it's homogeneous because all of this stuff on the right does not contain our unknown xn. We could compute that fairly easily. We're just isolating the unknown parts. And the idea is this allows us to use linearity tricks again. So again, we'll guess. So we've already seen how to solve something like this. Guess x to the n is equal to lambda to the n. Plugging this in, we'll get something after dividing by lambda to the n. We'll get a lambda squared plus 5 lambda plus 6 is equal to 0. So that's what's happening, the dots there, plugging it in, divided by lambda to the n. And we can factor this maybe a little bit easier. This is, we've already seen something like this, lambda plus 2 and lambda plus 3 equal to 0. It's a factorization. So this tells us that lambda is equal to -2 or -3. And this tells us that our general solution, xn, will look something like -2 to the n plus -3 to the n, with some unknown coefficients. But maybe we should be a little bit careful here. Let's call this x homogeneous. Maybe we'll call it x sub n, but then, all right, HOM up there. This is just the solution to the homogeneous part. Okay. Excuse me. Just as in differential equations, once we have a homogeneous part, we then look for a particular solution. This can be done really in either order. So if we look back to, so we look for a particular solution. So let's go back to xn plus 2 plus 5 xn plus 1 plus 6xn is equal to 24n plus 2. Okay, great. Now we just want to find one solution that will make this true. And there are several ways to go about this, just as there are in ordinary differential equations. But one maybe fairly straightforward method is just to notice that the right-hand side is a polynomial. In this case, it's a nice linear polynomial. And so if we were to plug in some formula, if we had some function of n that we plug into these things on the left, they have to combine in such a way, in this linear way, to give us another polynomial, and in fact, a linear polynomial. There's not very many functions that can do that. For instance, suppose I plugged in an exponential here. Well, combining exponentials is probably not going to give me a nice linear function. Or if we plugged in something crazier like sine or cosine or log or something, we're not going to add functions like that together and get a linear polynomial. So we'll just guess that the solution itself. I mean, on the other hand, notice if I plugged in a polynomial and did these operations, I should get out a polynomial. And moreover, a polynomial probably of the same order. So let's guess that xn is of the form a n plus b, something like that. And just plugging this in, we'll see what happens. So if we plug it in, so then of course xn plus 1 is a n plus 1 plus b and xn plus 2. So our only guess is this. The rest follow. This is a n plus 2 plus b, like that. And then we'll plug in to get, well, our xn plus 2 is a times n plus 2 plus b plus 5 times a n plus 1 plus b plus 6 just a n plus b, and that's supposed to equal 24n plus 2. So by the way, this is sometimes called the method of undetermined coefficients, both here and in setting with differential equations. If we now combine the coefficients, let's combine the coefficients on n and also the constant terms. So here, what's multiplying n? Well, we have a times n, so we get an a there. Here we have 5a times n, so plus 5a. And here we have 6a times n. Oops, excuse me. There we go. My apologies. Plus 6a, all those multiplied by n. And then for the nonlinear terms, excuse me, for the constant terms, we have, don't forget this one, we have 2 times a and then plus b. Here we have 5a and then plus 5b and then plus 6b. And again, all that is supposed to equal 24n plus 2. But notice this is just a polynomial in n, so the coefficients should agree. So we have that, maybe let's label a couple of things just to be clear. This was xn plus 2, this was xn plus 1, and this is xn. This thing is supposed to equal 24, equating with things on the left, and this one is supposed to equal 2, equating with the 2, excuse me, on the right. Okay, so from this one, notice that that's just a nice function of a, that's just 12a, and it's supposed to equal 24, which tells us that a is equal to 2. Excuse me. For the next one, we can just substitute a directly in, now that we know that a is 2. And I'll simplify this a little bit, but you can check it if you like. So that's coming from this. And I guess using A is equal to 2, we get 14 plus 12b is equal to 2 on the right-hand side. And so solving here, subtract the 14, we get minus 12, so b is equal to -1. So that tells us that our general solution is xn, that is the particular solution, xn, which was an plus b, is just 2n minus 1. Great. So our general solution, and this will be the homogeneous part plus the particular part, will look like this. Xn, and sorry, I'm just going to reuse the label xn here. Maybe I could call this something like xn particular. I'll call it part. Oh, excuse me. Keep bumping things there. So xn will be maybe xn homogeneous plus xn part. So that tells us that xn is, well, before we got a times -2 to the n plus b times -3 to the n. That's the homogeneous part. And then the particular part looks like that to solve the full equation. Now, if initial conditions are given, right, we would only plug them in now. Sometimes students will make a mistake of plugging in the initial condition to the homogeneous part, which won't make sense because it's not a solution to the original equation. Sometimes students also ask, why do we need the homogeneous part? The idea is that gives us, so the homogeneous part gives us enough degrees of freedom. That is, we have these two variables which can be used to match the initial condition, but this is not enough of this doesn't solve the original equation. It's only the whole thing altogether that solves the original equation. Okay, but that's a way to solve homogeneous equations. Of course, there are many varieties of those. You could have many different right-hand sides, all that kind of stuff. But for at least these linear homogeneous equations, or inhomogeneous equations, excuse me, in this case, we get some nice closed form solutions. Okay, another situation that arises pretty commonly in differential equations is that the notion of a repeated root. And let's just see a nice example of that. So consider the recurrence relation, 6n plus 1 and minus 9xn. Excuse me. And here I will give some initial conditions. So x0 will be 2 and x1 will be 0. And let's see how to handle this. Well, again, we'll guess the solution is xn is lambda to the n, and we'll plug in to the recurrence relation and get lambda squared after dividing by lambda to the n is equal to 6 lambda minus 9. If we get everything on one side, we get a quadratic equation of this form, and factoring that gives us a repeated root. So we have lambda is equal to 3, but no other solution. And this becomes a problem because if we try to guess, so right, we have a repeated root. If we plug that in, that is, if we just sort of proceed naively, we would have xn would be 3 to the n times some unknown coefficient plus b times the other root, but the other root is the same root, times 3 to the n. And all of a sudden, these two terms combine, we just get a general unknown a plus b. So this would not be enough to match initial conditions. so in order to do that, we need a linearly independent solution. And you might guess what the way to do that in coming from differential equations. If you remember, if you have a repeated root, let's say the root again was 3, if you have a repeated root in differential equations, e to the 3t, you multiplying by t turns out to be the right solution. And there are many ways to argue that. But we'll do an analogy here by putting an n there. And so you can, so try it, show that n times 3 to the n solves the relation. So if you plug it in, right, solves the this relation, 6n plus 1 and then minus 9xn. So I would encourage you to give that a try, just to increase your skills a little bit. See what happens when you plug this in. And the idea there is that as you're taking these, as you're looking at these these sort of shifts here, you get a reproduction of the 3 to the n parts, and it's enough to make this relationship true. So but let's just take it for now that you've checked that and everything seems good. Let's now solve. So then let's say solve for A and B using initial conditions. All right, so to do that, we take x0 and we will put this in for, so x0 on the one hand by the initial condition was equal to 2. On the other hand, by our formula, this is a times 3 to the 0 plus b times 0 times 3 to the 0. And that just boils down to a. So we get immediately that a is equal to 2. That's kind of nice. The next one is the initial condition was just 1 there, but that's for x1. Plugging that in, we get a times 3 to the 1 plus b times 1 times 3 to the 1. And that just works out to 3a plus 3b. That being equal to 0 tells us that we must have b is equal to negative a, which is equal to negative 2. So we get b fairly quickly as well. And this tells us that our solution to the whole system, which also handles the initial conditions, will be 2 times 3 to the n minus 2 times n times 3 to the n, like that. So this is our final solution for this situation. Of course, and I hope you can see that we could do all kinds of variations on this. We could have a repeated root with inhomogeneity on the right-hand side, and there you have to get you have to worry about things like resonances, and all of that, all that framework from differential equations carries over pretty analogously to this case. But this is an area that's not often maybe explored or presented in kind of say some, at least a differential equations course, and it's something that's sometimes missed. So I think it's just a nice piece of mathematics here for us to take a look at, and can be pretty useful in certain circumstances to close these recurrence relations. I want to look at one more way to handle these. So a different way, let's say a different approach. And that's, let's revisit. So let's again look at the Fibonacci sequence, partly because we've already looked at it. And so when we get our final answer, we can have some reassurance that this new method will work. So this is second order recurrence relation. But you might remember, so recall from ODEs, if you have something like, let's just say y double prime plus 5y prime plus 6y equals 0, then we often will set something like x equal to y prime, and then we get x prime is equal to y double prime, which is equal to minus 5y prime minus 6y. And y prime itself can be thought of as an x. We also have, of course, y prime is equal to x. And so we get first order system. First order, let's just say 2 by 2 system. X prime equals this guy and y prime is equal to that. Well, we can do something pretty similar in this case, but we might ask, what is the kind of analog of getting a new variable here? Well, it turns out it's maybe even more straightforward than in the ODE form. We'll just rewrite the relation fn plus 1 equals fn plus 1. So that seems like we've done nothing, but it turns out, well, as you'll see, this will be a pretty nice choice, because then we can write this as fn plus 2, fn plus 1 equals, so we'll now think about these as a vector. So here we're going up in dimensions, and again, in this case, we're going to go up in dimension. Fn plus 1 plus fn, and then fn plus 1 again. But notice that we can write this as a matrix times some unknown vector. So here we have fn plus 1 and fn for a vector. Notice that's one step lower than this. And here the matrix will be 1, 1, 1, and then 0. All right, so if we call this guy, let's call this one A. Call this guy, let's call it big F vector at the nth position. And this guy can be big F, then this will be big F at the n plus first position. So we get, so we write this as big Fn is equal to A times big Fn. So big Fn at n plus 1 is equal to A at Fn. Yeah. So, and our initial conditions, of course, will be just, say, F0, which is a little f1, little f0. That'll just be the vector 1, 0. So our initial data is just given by a vector. So this is now a first order recurrence relationship because we only need the previous piece of information, but that piece of information is now two-dimensional. So to give you F0 or F1 or whatever, I have to give you two pieces of information. So we've just really rewritten things. But now, notice that we get something kind of nice out of this. So let's try to compute F1. Well, that would just be A times F0, which is 1, 1, 1, 0 times 1, 0, and we get there 1, 1. So we are starting to see the Fibonacci numbers just pop out there, kind of two at a time now. F2, well, that would be A times F1, but notice that that's A times F0, which is A squared times F0. And I think you can see, just as we had before, that we can solve this pretty immediately by just writing this as each time we get another A, factor of A showing up. So the general case just looks like our first order recurrence relationship where we get A to a power. The difference is now that A is a matrix. So the differential equations analogy here is the matrix exponential. But here we just get a matrix power. So it's arguably maybe a little bit nicer to compute this because we don't have some like transcendental function or infinite series or something. We just want to compute A to the power. But in practice, we compute this in a pretty similar way. So the idea is to use, we can compute a general matrix power using the Jordan normal form of a matrix. But in this case, A is just diagonal. So we want, so idea to compute A to the n, let's say nicely, because of course one option is just to do what we did before, just multiply A by A by A by A. But this is not really like a closed form where we can just plug in, n is equal to 1,000,000 or something. We would have to kind of do this iteratively. Now we'd like to have some type of closed form. So we would like to write it as PDP inverse because A, as we'll see, has distinct eigenvalues. And so the A can be, the Jordan form just becomes a nice diagonal matrix. Okay, so let's try to find let's look to the eigenvalues of A. Remember that A is just this matrix 1, 1, 1, 0. Pretty straightforward to find the eigenvalues. It turns out that lambda 1 is 1 plus square root of 5 divided by 2, which is just our golden ratio phi coming up again. Kind of interesting. And lambda 2, the other eigenvalue, is 1 minus square root of 5 divided by 2, and that's our phi bar. Okay, so we're seeing these two characters show up again. Also, eigenvectors, and we'll use these same numbers for them. V1 is phi and then 1, and V2, the one corresponding to lambda 2, is phi bar and 1. And so A is equal to, well, we wanted to write it as PDP inverse. So P is just, we put these eigenvectors together. D is the corresponding eigenvalues in the same order. So let's write just phi and phi bar, 0, 0. And then our P inverse turns out to be, well, it's 1 over the square root of 5, which is the determinant of P. So you can just use the normal determinant formula for a 2 by 2 to get this. This is phi divided by root 5, excuse me, minus phi bar divided by root 5, and negative 1 divided by root 5. The form of it isn't particularly important, but this is P, D, and P inverse. All right, so that means that notice that we take A squared, that's P, D, P inverse times P, D, P inverse. But these inner P's will cancel because we have P inverse times P. And so we just get P times D squared, P inverse, and so on, all the way down through A to the N will be P, T to the N, P inverse. But that is just that P matrix. When you take D to, when you take a diagonal matrix to an nth power, you just get phi to the N. Now you get the diagonal entries to the N with zeros on the off diagonal. So that's arguably much nicer to compute than just iterating this thing many times. Excuse me, that was supposed to be an N. And so that means that our Fn thing, which was just A to the N times F0, that is just this P diagonal matrix. I'll just write that. P inverse times our 1, 0 for the general setup. And one can just compute what this is. And remember that this is Fn plus 1 and Fn. So reading off after doing the computations, and maybe, I mean, the computations are pretty straightforward, but a little bit lengthy. So maybe I won't show them right now. But the lower Fn there, after cranking out all the computations, just gives you back the usual Binet formula, which I'll let you check for yourself. So we see we get the same thing, but by somewhat slightly different way of going about it. And arguably, this is maybe more mathematically satisfying in that we're not at any point making a guess as to the form of the solution. We're just noticing that we have this matrix iteration and iterating from there. So this is sort of a different way to handle these recurrent relationships, which ultimately is somewhat equivalent. But sometimes it can be good to use one formula. Sometimes it can be good to use one approach. Sometimes it can be good to use another approach. Notice that ultimately both of them, in both cases, you're having to solve a polynomial. In this case, when we find the eigenvalues of the matrix, there's a polynomial solve that comes up there that I've skipped here. And in the original case, you're having to solve a polynomial. So we don't really escape at some point having to solve a polynomial, but we just have a few different ways of seeing these two things. So thanks for your attention. Next, we'll be on to nonlinear systems. And just to emphasize, the whole all of the construction here was based on this idea of superposition. That is, that I can take two solutions and combine them to make another solution, right? We did this again and again, taking two solutions and combining them to make another solution. Almost by definition, nonlinear equations are those equations for which this trick doesn't work. Nonlinear equations are also, as mentioned earlier, can exhibit all kinds of crazy behaviors like chaos and interesting things, even for pretty simple, pretty tame examples. So we'll take a look at that next time. Thank you.